Dear participants, I am very thankful towards you who joined this solar cells and LED simulations webinar. First, I will show you the presentations parts about the company and products and related to the SETFOS and LAOSS softwares. Then I will show directly the SETFOS softwares, how you can simulate different properties for the solar cells and OLED as well as. So it is the impulse technology which provide the cutting technology of the next generations nanoscale materials and device, semiconductor device, TCAD and quantum technology, spin qubits, quantum dot semiconductor device simulation software for the education, commercial and research and development sectors in India. And we have the number of the partnerships like FLUXiM, Nano Academy Technology, and AJW. And you can see near the different institutes like NICE, IIT Bombay, VIT, IIT Roorkee, SRMs. Number of the institute use different softwares, and we have the different products. Like you can see, SETFOS. It is just simulation softwares for the solar cells, organic, inorganics, and different LED. So you can use this SETFOS softwares and large softwares. It is a simulation software for the upscaling to large area device in OLED and solar cells, analyze electrical losses in large area electrode. So this webinar related to the SETFOS and large softwares, but who is interested in the different other softwares like materials, molecules, so spin qubit material simulation software. So you can do and use these different softwares like nanodecals. Nanodecal, it is used for the material and device simulations and totally based for the atomic scales modeling for quantums and nanomaterials. Rescue softwares, it is used for the material simulations parts. QTCAD is one of the softwares for the spin qubit material simulations. And nanoskim softwares, DSPA, BDF, and more. We have the different softwares that you can use, like DSPA softwares. It is a first principal density functional theory that calculates that atomistic material simulations and operate it plane wave basic sets. So you can use this software as BDF. It is used for the quantum chemistry, totally for the molecular analysis, and for the post processing for the molecules, you can use that moment. So we have the number of the softwares. And as we can discuss in here the SETFOS and LAOSS softwares, but PEOS, PHLOS, LITOS, and LITOS lights. We have that software as well as the equipments. Like PEOS, it is used for the electrical characterization of the OLED and solar cells that used for the transient photoluminescence and transient photocurrents. And one of the PHLOS, it is used for the angular luminescence spectrometer to characterize light emitting device. Simple word we can say angle dependent electroluminescence and photoluminescence measurements. And LITOS, it is used for this degradation analysis of the LED. Also, you can use advanced LED stability lifetime measurement systems and LITOS lights. It used for the like LED designs, but parallel JV and stability measurements on organic perovskite solar cell and perovskite silicon tandem solar cell. That you can say it is advanced version of the LITOS. Number of the institutes like IIT Madras, IIT Bombay, IIT Delhi, they are using the SETFOS softwares. They also publish their papers. And this softwares, that parent company FLUXiM AG, it is a Switzerland-based company that develops scientific tools that help to boost our research and developments. It is simulation software. It is scaling for the large area measurements, hardware of the OLED, perovskite solar cells, and OPV. It outcome of the institute that every software is based on the sum of the physics or university, like Dr. Bisestra founded that FLUXiM AG as a spin-off company that have the 20 years plus in the industry as well as the academic basis. They have the 200 publications. Sound material device model have been successfully validated by dedicated experiments. You can also integrate SETFOS and LAOSS, combined characterization of the DC, AC, and transient regions. Our softwares and instruments you can see in here that we have discussed. We will focus in here the SETFOS softwares. It is a simulation software for the optical and electrical modeling of semiconductor device, designing LED, solar cells based on the organic semiconductors and quantum dots. Fitting and optimization algorithm also included in here. Operating systems, Windows, Linux, macOS, you can use this software. Multi-threading ensure high-speed computations at the single time. You can run different programs in here and projects. SETFOS uses variety of models. Like every software follows some of the theory, some of the models. So SETFOS that follow that part like dipole emission models. It helps to predict the light emission characteristics of OLED. Transfer matrix formations that help to calculate photon flux across the solar cells. Drift diffusion modules models charge transports and recombinations. My scattering optimize the concentrations and refractive index of scattering particles. SETFOS, it is a simulation software, but that data you can also verify in the experimental way, and experimental data you can also collect and provide in the SETFOS. It helps to visualize your results like different researchers with the valuable insight and trend the predictions. And you can see here some of the emissions, depth diffusion, absorption, and advanced optics. But SETFOS like divided in the 5 modules. If you want to only work for the solar cells or OLED thermal properties, so you can use different modules according to your choice. Like you can see, emission modules. It helps to simulate light emissions from the OLED and LED, calculate outcoupling efficiency, angular distributions, optimize emissions for the maximum brightness and efficiency. OLED type of property like emission properties you can calculate in the SETFOS softwares. So they have the different module. When you want to calculate optical properties, so you can move toward the absorption modules. It helps to calculate optical data, include interference effects, wave optics effect, analyze absorption profile for the organic perovskite, and basically say solar cells. And drift diffusion, it helps to calculate electrical properties at the simple word we can say. And inside they have too much large like steady state, transient, AC, intensity modulated photocurrent or voltage spectroscopy. Simulate charge transports using drift diffusion models in here. Solve poisons and continuity equations self-consistently. Evaluate carrier density. Something that have given, but when I open the SETFOS software, so I will show how you can use. It is a scattering modules, also known as advanced optics. Model scattering features in the texture or rough layer. Solve wave optics for the coherent, incoherent. Analyze near field anisotropic optical effects. New modules that have added in the newest versions, thermal modules. It calculate temperatures, distribution in the device, include joule heating, thermal boundary conditions, evaluate thermal management and device reliability. So different modules they have divided, and when the project you start work on this, so you can use each of the modules, and it is a graphical user interface of the SETFOS softwares. Easy access their device structure that you can create. So the device design, material parameters, and working file simulation outputs. Like you can see near that examples where you can create your layer structures, all the inputs and features that you can provide one by one for the each of the layer you can do in here. Files that you can import material parameters, electrical material parameters in here. It is a stack preview and it is an energy level. At the top side, different modules given. Easy access of the library of the simulation examples, that is the examples. Material property in these tabs you can see. Multiple simulations can run in the parallel. Key graph results that have fast generated, and you can also export your results. Scripts you can also write because it is a fully compatible with Python as well as solar cell modeling and parameter shifts and device optimizations. Like if you're working on the solar cells, so at the module wise they have divided and different properties you can calculate. Some of the properties that have given like calculate source circuit current, open circuit voltage, fill factor, maximum power density, power conversion efficiency. Specific for the organic, quantum dot, perovskite solar cell, optimize the device for that spectrum files like default spectrum files that have given. You can provide in the absorptions modules, curve fitting, parameter extractions, optimizations tab that have given where you can extract your parameters. So that have different tabs given. Understanding the origin of the hysteresis of the perovskite solar cells, AC simulation, transient experiment, photoclean, easy to couple with electrical characterization with the system chaos, designing anti-reflections coatings or transparent solar cells. So for the solar cell modeling, some of the things that I've given. If you want to shift your parameter with the fixed range, fixed target, so you can do. You can also extract your parameters using optimization tabs. What is the workflow that you can follow for the solar cell simulation? First, you can create the device layer stacks. Then you can provide optical data one by one, like that can be created in here. Set optical properties, like absorption module you can active and one by one, each of the absorptions or optical data you can provide. Then you can simulate for the optical parameters. But if you want to give any of the electrical parameters like energy level that I have created, HOMO, LUMO value, or electrical parameters, mobility, anions and cations, and defect density, traps parameters like, so you can provide one by one in the electrical modules, like any other something that given recombination, traps, and contacts. Then you can run your simulations after the providing inputs. You can also analyze your results, and then you can export your results in the data forms, in the image form, and whole projects you can also import. It is a 4-terminal tandem solar cells. Like you, you can create 2 terminals in the one time, but for the 4 terminals, you can create 2 projects for the top cell data. Then you can collect that filters of cells, transmitted files, and then you can simulate a bottom cell as well as in here. So top cells results and bottom cells results you can see, and that energy levels that have given. When you move toward this 4 terminals of cell efficiency results, you can see it for the bottom cells result, power conversion efficiency 0.078, and that's top cell results efficiency. And it for the 2 terminals that we have seen in the tutorials. And 4 terminal efficiency results you can see, you can plus this efficiency top and bottom that have the separate result. You can compare your result in the SETFOS as well as in here, and it is a 2 terminal efficiency. This results, it is a 2 terminal and it is a 4 terminal. What is the actually usage of the SETFOS softwares? First, you can create or designs, research and developments, like you can publish your papers, different publications that I've given, like IIT Roorkee, IIT Madras, Berhampur. So number of the institutes that have published their papers. So we have attached some of the publications in here. You can design your solar cells. You can extract your results in here. When you move toward the visual analysis, like if you want to see that results, so They are divided in the tabs wise, like optical data, spectral data, numerics data, optical integrated, and passive optics. Moves toward the optical results, like for the absorptions, you can see this type of results. When you move toward the electricals, so they have given the electrical files separately. Same for scattering modules, emission modules, optimizations. So one by one, you can see each of the tabs and that each of the graphs. We have attached some of the graphs in here, like layer absorption, absorption profile, emission, and AC current density. So, but when you move toward the SETFOS result part, so that tabs have given each of the graphs and their results you can see. Highest efficiency of the perovskite solar cells, like perovskite single junction solar cells, perovskite silicon tandem solar cell, and perovskite tandems. What is the area, year, and institutes? So, like number of the company or institutes, they are working on the SETFOS software. It is a experimental results, but when they are using the SETFOS software, so they will give that process how you can enhance your power conversion efficiency, because simulation softwares always help and test one by one each of the results. So it attached some of the perovskites, what is the actually highest efficiency that they have gets with that area with this year. So it is a world records. And Longi are a SETFOS users, and they are using advanced simulation softwares to improve their perovskite based solar cells. What is the record efficiency of the perovskite silicon tandem solar cells? So we have attached one of the research page in here, that's result you can say, and you can see this the graphs for the crystalline silicon solar cells, and it is a perovskites, and it is single junctions perovskites. That's how they are increases, and you can see near the year like 14%, 16%. So SETFOS give the hints, and simulations results will provide that actually efficiency. So one by one they follow that, and then they use their experimentals as well as their SETFOS results. And Longi, it is the users, and they working on this, and highest efficiency they have gets for the perovskite silicon 34.85%, and it basically that's give the hint how SETFOS empower high efficiency solar cell research parts. So you can see that results, and it is said that benchmarks that SETFOS it is too much helpful toward that research, as well as this research you can use in the experimental. How can we overcome the Shockley-Cuser limits? So like a Shockley-Cuser limits that we can say not included that losses limits, and they calculate what is the theoretical maximum efficiency, so that provided in the SETFOS as well as, but when you provide the different parameters, so they limit that your power conversion efficiency. So that limits what can be the regions like high energy photons that emits, and that heat will lost in that, so that can be said thermalization's loss. Some of the energy loss in the transmission loss, like simple words that we can give: hot carrier solar cells, intermediate band gap solar cell, and multiple exciton generation. So that process can be helped to improve that your PC, that you can follow that steps. So in that simulation steps, they will provide that help, because each of the tabs that have given, so you can provide their inputs value, and then you can visualize one by one each of the steps. When you move toward the multi-junction solar cells or tandem solar cells, so we have that's 4 terminals, 2 terminals. So different junctions you can create in the SETFOS. softwares, and when you increases that efficiency, so it will beneficial toward that research parts, so that we have attached type of the solar cells in here. Number of the users working on the SETFOS and escape 1D, but they didn't get what is the actually difference. So basically SETFOS, it is a commercial software, and that have that supports more than 7 layers. In the escape 1D, they have only the 7 layers they have supported, but unlimited layer you can do. Transient simulations you can do in here, but escapes they can't do in the transient parts. Optical profiles results you can simulate. Roughness and scattering features, because they have the separate modules that have given. Hoping models you can also see in this, because interface they have divided in the 4 parts. So hoping features also included on these 4 parts. Parameter shifts, they have the also tabs. Signal analysis, supports and updates. So basically SETFOS, they have a lot of the features beyond the escape 1D. SETFOS applications you can see in here. SETFOS organic solar cells simulations and optimization of organic solar cells. Perovskite, heterojunctions, dye-sensitized solar cell, organic photodetector. So it is the applications parts of the SETFOS where you can create, you can design, you can simulate, and you can find different properties. And now we are using the SETFOS 0.0 version, but in the within 1 week that have get new version SETFOS 6.1, and that have advanced features that have comings like intensity modulated photo luminescence spectroscopy of an OLED for the perovskite, as well as external quantum efficiency of the perovskite silicon tandem solar cells that have the advanced features. This coming bifacial perovskite tandem solar cells, it is also coming. JV curve loss analysis of the perovskite tandem solar cells, tunnel oxide passivated contact solar cells, and doping induced tunnel junctions tandem solar cells. So in the new versions, different features are also coming. And number of the users that have questions related to that solar cells. So like what is the current highest efficiency of perovskite solar cells? So 26% that had noticed by that verified NRL. And which company holds the record? So Longi, it is a user of the SETFOS softwares, and it is continuously working on that SETFOS softwares. Tandem solar cell is more efficient because absorb different wavelengths of light with separate layer, reducing energy losses, increasing total PCE. Like we had discussed, cyclic user limits. For accurate optical and electrical simulation, Tandem are what only used. Researcher uses SETFOS, FLUXiM simulation platform for the thin film device. It widely applied in tandem optimizations workflow, external contact sensing matching, and current density predictions. That customers uses the SETFOS softwares. You can see at Madras, at Guwahati, Bombay, Dhanbad. So different DTU, it is the uses the SETFOS software. So number of the customer users. So now I'm going to open SETFOS softwares. It is the end of the presentations parts. Before start of the created one of the perovskite solar projects, First, I will introduce about the graphical user interface of the SETFOS. It is the GUI. At the top side, when you click on this, you can create your new simulations file. For the existing examples, you can move toward these tabs. If you want to save your projects, you can use both tabs, save or save as. Its viewpoints for the examples, layer stacks. It is a material database tabs. Number of the materials, refractive index files .nk that we can be say, you can see. It is well verified at the original publications and their data as well as. So SETFOS also attach their library. So it is a material database library. It is a passive optics module, simple for the calculation reflectance, transmittance, and absorptions. Like we discussed about the module, so it is a 5 module. It is a absorption modules. When you activate absorption, so absorption module will active in here. It is a emission modules. When you click on the emission modules, so emissive properties you can calculate and emission modules activate in here. It is a scattering modules. When you click on this scattering, so scattering modules will activate. It is a electrical like drift fusion modules. When you click on this, so drift fusion module will active. It is a thermal modules. When you click on this, so thermal properties you can calculate it from this module. So it is a 5 modules of the SETFOS software. When you activate emissions or different features, it is a master equation mode, advanced OLED calculations, forest and distance or different properties for that small particles you can also do in here, master equations modes. We have discussed about the shift and optimization. So it is a shift tabs where you can shift different properties. And it is a optimization mode where you can extract your parameters. It is a fit emission zones, like emission zone fit also can be saved for the emission extraction parameters you can use. So that different tabs that have given. Here you can provide input parameters or different files. You can use these tabs. It is a general tabs when you activate for each of the layer. It is stack preview or energy level that input you have provided. So automatics they will created in this side. So it is a GUI of that we can discuss. It is a script. It is a console view, and it is a result. When I will simulate the results, so you can see that tab will also be active only for the result analysis. So now I'm going to create one of the simple perovskite solar example. At bottom side, you can see you can add unlimited layer in here, and then you can provide one by one each of the layer name. First, I want to provide in here like air, top, like simple theory that have worked for the solar cells. So you can follow at the same one by one. You can provide the layer, then you can provide the optical data, input parameters. So then you can simulate. So first we need to create the layer and thickness. So that will create the stack preview according to this glass. One of the conducting oxide you can take ITO. whole transports layer. It depends on the users, which type of STL layer, ETL layer that you want to take. So you can consider according to this. One of the most active like perovskite, one of the active absorber layer you can take. ETL layer you can consider C60. Electron buffer layer, copper like metal contacts. And follow that one of the examples. So like this, you can create one of the layer stacks. If users that have choice the different solar cell or different perovskite projects, so they can select according to this. And then you can provide a one by one thickness. Like for the air, you can set as the 0, 0. But for the glass, you can set 0.5. Unit you can see in here, different unit you can select. ITO you can give 150 nm. For the STL you can give 10. It is the most active observer, so you can take large thickness, so they will absorb. C60 you can select 20. As for the copper, it can be same 100. Now you can see at this stack preview sites, layer stacks that have created automatically here. And it is just a layer name and thickness that you have provided. But now you need to provide one by one absorptions or optical parameters. So you can activate that modules absorptions. And after this, you can provide in here wavelength dependence files, that layer which is wavelength dependence. So one by one, you can provide in the refractive index files. You can click .nk. You can see different files that have given. If you want to import constant bipresence or want to put this data, you can put tabulated.nk. If you want to provide separate N and separate K files, analytical dispersions, effective medium dispersion files, approximations. So different files you can provide. And in here you can see different .nk files that have given in here. It is a library of the SETFOS that have existing library for the refractive index. It supported that .nk, and you can see it is a ITO. Now you are providing one by one each layer data. So first you can click on this I in the keyboards, and then you can import ITO.nk, and you can see that have supported .nk. And if you want to see what is the actually parameter that have given in here, you can see it is a wavelength, it is a N, and it is a K data. You can see. So it is also editable. If someone have that's your own data, your own files you want to put, so you can directly edit in the notepad, and you can also edit in here. So it depends on the users. You can create your own file or material data files you want to import or export. So you can also do from these sites. So one by one you can import. So which layer is wavelength dependent? Because when you move toward the optical data, so it is a most important part. For the perovskite, you can see we have different perovskite files you can import. It depends on the users, like they have selected one of the layer stacks or file, so they can search in the material database and then you can collect. If they are not available in the material database, so you can collect from the material softwares and then you can create your own files. Now we have imported each of the reflective index files one by one in here. If you move toward the absorption settings, like it is a file input parameters, but for the modules where you can simulate your results according to the different spectrum files, different range that you can select in here. So you can do in here. Like if you want to shift for the single wavelength parameters, only want to simulate this, and when you move toward this, you can see intensity and wavelength, default optic settings that you have set, and different spectrums. Like one of the spectrum AM 1.5 that follow, but if you have the different settings, you can do wavelength on energy shifts. You can do, and in the absorptions module, so white spectrum files and important parameters that location and date and times, like energy yield calculations and the fixed date and times calculations for latitude, longitude, and elevations, date and times. You can provide times, time zone that have given module orientations, weather, cloud cover, cloud is 0, that means sky is clear. You can select 1 or not. So you can select. So it is a absorption settings where you can set your own parameter. Ranges, according to this ranges, result will come. If you change the different range, so that result will change. Like I've selected in the 300 to 800. And when you move toward this, like layer stacks, or you can give another simple name. You can see it is a script that are Python supported, but you can also edit that script. But it is a simple GUI where you can put one by one each of the input. So it is a most easy part in here. It is a console view where you can see your project timings, layer stacks, what are the setting that you have done, time supports, memory settings. So different features or different things you can see in here, reflected color of your project. When you click on the absorptions profile, you can see, you can zoom like this. It is absorptions profile result. You click on this and height, ranges, x-axis, y-axis that have given, tools, files. If you want to import image, you can see different formats that have supported. You can import. If you want to see that data, what is the actually data of this, we can collect where you want to save. Energy flux. That 550 you have selected, and it is the settings, iterates, phase, wave, optics, features, reflective index. It is only for the absorption. So optical data that you can see in here, absorptions, same you can do collect curve or things. Layer absorptions, you can see glass, ITO, PTA, each of the layer you can see in here, you can see perovskite C60, reflectance, stat contributions, and transmissions file. So it for the opticals, and what is the actually optical key figures that they can provide. So some of the result optical key figures that have given in here, but it's just for the absorptions module calculations parts. But when you activate electrical module, so you can click on the electrical modules and you can see different types that have active in here. Electrode, semiconductings. So now you can provide in here one by one electrical data. So you can select in here the electrode work functions first. So like we are going to select as a ITO, you can select, but users that have that results or they have their own project. So it depends on that which type of electrode or active materials or electrical materials they want select. So they can do injections models like ohmic, thermionic, organic. So that have given boundary conditions. And I'm just selecting the ITO work functions. You can select in here that 5.4 at for the project. And in here that bottom sides electrode you can select and provide in here that value 4. And in bottom side you can see layer between electrode must be semiconducting. So one by one you can activate in between the semiconducting layer, because when you selected that ITO or top and bottom, so you need to give near the semiconducting layer, it will show that error. When you move
Hello.
toward the semi, yes ma'am.
Good afternoon. So, which
Yes ma'am.
material you consider the for ETL layer and HTL layer in that simulation?
I've selected as a PTA as a STL layer and C60 as a ETL layer.
Sir, PTA, can you explain full form the material name?
PTA. 1 minute.
Also, BPC,
Like,
you mentioned BCP. Which
yes ma'am.
material?
Like we have selected as that C60 as you know ETL, but PTA is one of the polybis 4-phenyl 2,4,6 trimethyl phenyl amine. It is a members of the polytriamides, ma'am.
Okay.
Amine family, basically you can say organic polymer
So,
semiconductor.
hello, sir. Why did you select PTAA as a ETL? We can use also TiO2, ZNO
Yes, sir.
as a.
And also spirometer.
Yes, ma'am, you can use like TiO2 or different HTL layers. As we mentioned in here, the HTL layers. So you can, like we mentioned in the HTL. So you can import their refractive index files and semiconducting files. I'm just follow the example. So I just selected this PTA for the perovskite, but it depends on the users. Like if you want to select different HTL layers, you can select. It's not mandatory that you need to select only this PTA or this ETL, C60L. I'm just follow that example, ma'am.
Okay, sir, one more thing.
Uh,
You mentioned uh, air top infinite interconnected. What is that?
what, ma'am?
First, air top. It is the
Air top.
top bottom or
Yes, ma'am. It is a
front
air
side or
top,
back side?
air top as we have selected and air bottom as we have selected. If you select the same, so it will show the error for the software. So we just select air tops as the one of the layer, air bottom. मतलब it is a environments for that we have symbols.
Is this any parameter you mentioned
No.
infinite?
It is not a parameter. I'm just given that layer name. Like you created
Okay.
the solar cell one up, so for the environmental basis that we have provided.
Sir,
We not
can you more explain in every layers? Because I didn't understand anything.
like one by one I can explain to you, ma'am.
Yeah,
Yeah,
yeah. And I
like
hope everyone also,
no, not an issue, ma'am. I will explain.
because I have used Atlas Caps 1D and uh, I didn't use that software, but I use Scaps 1D and Atlas. So I'm familiar with the simulation process. That's why I have more questions.
Like softwares that totally working on that theory parts, ma'am. So we have only selected basically on that example part. So I can explain one by one so that you
Okay.
can understand. Like for you going to create one of the solar cells right now. So
Okay.
for solar cells, you need to as set as the environments or different things. So air as a top layer that working, but glass, like glass, it is a mechanical substrates and transparent productive window. Just for this productive window that you can say it is a transparent. So therefore we will take very less thickness,
Okay.
0.5, providing the robust foundations or nanoscale thin film to deposit on it.
Yeah,
And
yeah. Which methods you use? Spin coating or anything else?
in here, that's a method that we have. It is a drip diffusion that we have follow that solvers, but layers
Okay.
or things that totally working on theory basis. You
Sir,
can say.
actually, I am also using Scapes 1D. So in that
Yeah.
software, we are using FT glass as a conducting layer. Okay. So why
No,
in
ma'am,
this?
one more time, ma'am. One more time. It is not audible.
Yeah, am I audible?
Yes, ma'am. Yes, ma'am. Please.
Yes, actually, I'm using Scapes 1D software. In that
Okay, ma'am.
software, we are using as a front contact layer, FT or ITO. We are using as a front contact layer. So
Okay.
why it is using glass and after that ITO, because ITO is also a glass. No, yeah, it is coating glass. So is that necessary to use glass and ITO separately?
Like, ma'am, you have taken that only the FTO as a conducting that you have discussed. You can
Hmm.
basically use separately. You can also remove that glass, not that mandatory parts. But if you uses the glass as that's one of that transparent protective window for the solar cells, and
Hmm.
ITO it is a one of the also transparent conducting oxides. It is also one of the conducting oxide that you can select. It can also be selected as an environment. Like ITO in here, that's in the glass, you place the FTO. So it is also one of the conducting oxides. So you can give in here the FTO and then you can also import their parameters, ma'am.
Okay. So we
It,
have to replace glass with FTO, or we can remove one of those ITO or
uh,
glass.
you can remove, because we have the also a separate project for the FTO as well, as where glass and FTO both are used, and sometimes glass also used. Some of the like researchers, they are working on this, so they have the knowledge for each of the things like
Sure,
glass,
sure.
FTO, so they follow that each of the criteria. But we have the different projects, ma'am. Like if you replace this glass, you can use FTO as well as.
But
But
we
when the
cannot use FTO and ITO both at a time, no?
in place, you can use, in this place
If
you
we
can use,
if we are use glass and FTO, it's affected for efficiency generation.
maybe when you provided that results, like they have the separate effect, like they are not selecting any of that parameters, we selected at the constants as per the examples. But when you import the FTO, you provided that refractive index files, or so they will definitely as the wavelength or parameters, because the sunlight will fall, so maybe that provided the some of the effects, because you imported that input parameters, right, ma'am?
Okay,
Yes.
okay. Thank
Because
you.
when you provided the lights or different things at the top side, maybe it might be bottom side as well as. So they follow that criteria, so they will definitely affect on that efficiency parts. I'm just selecting any other constant therefore. Only the thickness value that we have provided,
Okay, okay.
right, ma'am? And like
Yes, sir. Sure.
HTLs in here that working as a whole transport layer. So it is a ultra thin layer designed for the highest molecular orbitals energy level that can be set. It cleanly extract the holes from the active layers and route them to the ITO. Like they will extract and then it route for that holes to the towards the ITO. Like we have selected the ITO as a node in here, and it block the electrons as well as. So therefore we selected at the HTLs. They help to pass that holes and block that electrons. And it is opposite process for the C60. And
So
perovskite is a,
perovskite as a use as a absorber layer.
yes, ma'am. Yes, it is
Okay,
basically working as the active light absorbing semiconducting layer. Right, ma'am?
okay, okay. Thank you.
So that's a layer and step you have follow. They follow the same criteria, not different for the, it follow the same theory parts, man. Because not only this project, we just follow the examples. When you move toward the more big major project like 2 terminal, 4 terminals, so they have also that different effect, because it is a simulation software. Like in here we move toward that 1 minute, it will displace.
Hello.
Yes, ma'am. Yes, sir.
Could you please share the software link in the comment section? Or...
Sir, I will say, inform you about this softwares or different things after the session, sir.
Okay.
Can we use AZO in place of ITO?
Like you can see, man, there's projects where you use different layers, and when you move toward the more 2 terminals and 4 terminals, I will also show you.
Hello, sir. Actually,
Yes.
I missed the last 1 hour conversation, so I just joined 5 minutes ago. So I don't
Uh,
know this software is free or what? I mean, how can I access this software? I didn't
yeah,
miss that part. Yes.
it is a commercial software, ma'am.
Okay.
It is a commercial software. So you need to
Okay.
contact after the session if you want to purchase or anything else you want to do. So you can see, ma'am,
Okay.
like in the previous questions, they have only the simple selection that we are do. But when you move toward this, you can also change the different polarity and different selections according to the layer wise. So not only these layers, the simple projects, but when you move toward the different projects, so theory parts are different features, interface, tunnelings, different things that will included. So then you will understand. So because in the escapes, very limited features maybe can be said, but any other transient, steady states, AC, a lot of the anion and cations features, traps, defect density, different things included in here. So one by one, when I will explain, so it will easy towards you, then you can understand.
Sir, it is more reliable for experimental devices or only
Uh,
theoretical?
Yes, ma'am. That in the PPT parts we have discussed Longi. It is one of that company that working on the solar cells that
Okay.
uses
You
that simulation data for the experimental work as well as.
okay?
So it is a
You
more
mentioned, yeah,
yes,
you
ma'am.
mentioned at perovskite efficiency is 26%. Is this experimental data or theoretical data?
Ma'am, it is a experimental that they have noticed.
Okay, okay. Please, can you share?
Like we at that electrode point of view. So we have selected that electrode. And like BCP we selected as the 4. So in between you need to select semiconducting. Semiconductings, it is a tabs, but when you move toward the semiconductings, you need to provide each of the layer and their data. Like 1 minute. You can see when you select toward the PTA, one of the HTA layers, imports, charge, excitant, traps, mobile ions, and recombinations. So one by one, you need to provide that value, energy levels, effective density, dielectric constants, acceptor, donor dopings, polarity. It not for the modules, but each for that layer value. Like in here, you selected that TiO2, SNO2. So value will change according to your projects or layer selections. And different mobility features that have included constant mobility, field dependent mobility, field temperature dependent mobility. So different features that have given. When you move toward the excitons, exciton means that electron and hole bind calculations, how the binding. So that tabs, different tabs and value you can provide in here. Not only the single excitons, like at this side you can see energy transfer rates from which layer to layers or tabs to tabs they have given, and excitant value for this PTA layer you can provide. Traps features like acceptor, donor, neutrals, like defect that is someone want to provide in the simple way. Trap density, energy distributions, energy electron capture rates, hole capture rates, and mobile ions like anion and cation calculations you can also do in here. You can also include it with the mobility features. And recombinations, different recombinations given, like 4 type recombinations given in here. So it is just a theory part, like someone working on this different. So they are too much aware about this, how their selections work for the Langevin, Auger, bimolecular, simplified. So they can select according to this. But SETFOS that have the existing library for the material. So you can also directly import PTA, you can see. So you can see that different library for that materials given.
Excuse me, sir.
Yes,
Sorry
ma'am.
for interruption. Sir,
No,
actually, I have to know how each factor is affecting. Like how the trap density parameter is affecting. What is the effect of that while we are modeling the layers?
Okay, ma'am. I will explain one by one. 1 minute. Like energy levels, you can see barriers, homolumo value in a band gap that you have listened, effective density in the unit wise that have given, dielectric constants, how that dopings with this layer, STL and perovskites, how they accept that holes and how they block that electron. So that features you can provide. Mobility, electric fields or different parameters, temperatures, how they are defects, so that you can provide. Excitants like electron and holes that generated some of that particles, but when they combine, so how much the heats or how much that losses they occur, so that you can provide in here. How like reduced decay rates, how they degrade, what is the generation efficiency, diffusion constants, saturation limits, and when you move toward the bottom sides, pair separations, how that charge transfers in between, and excitant quenching, that means forcefully of something that happened. It is too much inside that's for the particles and electrons, that how they moves for the electron and hole calculation basically, and their understanding how they behaves, how they moves, and what is the heat that generated and what the actually losses. So that value you can provide in the excitant. When you move toward the traps, so that means defect in this layer, any features, speed, that you want to give some speeds or barriers, they have some, so you can provide in the traps. Basically for the defect, any defect for this layer, so you can provide in here that features. And when you move toward the mobile ions, it's for the anion and cation calculation. If you want to do in here anion and cation, so you can activate that tabs, they will do. Recombinations, how they recombine molecules and holes. So according to that models, you can divide. But before the full information, it is too much theory parts. So their help or manuals that have given. And in that one by one, you can study each of the tabs, what is the actually meanings, because it's too much inside that theory, because it is too much big softwares, where each of the tabs that have the different meanings, like energy level, effective density. So when you go toward the inside, so that have a lot of that meanings. Like when you move to the perovskite, that have also the different energy level, different effective density, different homologo. Like we, if you imported excitant, it is a supported EM file. Like when imports PTA.em, you can see that value has been changed. Energy level selected, defective density. So value that will change according to this. When you select the perovskite, so one by one layer value that you can provide in here, like this, that have the different homolomo value, different effective density, different acceptor or donor doping value. So that has the different layer value that you can provide. Not only that, so whole solar cells that you created one by one, each of the layer, what is that actually electron and hole movements, what is the actually defects, how they recombine with the different electrons and holes. So one by one, that value you can provide if you have. And if you that value you are not, like you can check in the scripts, you can see energy levels, donor dopings, and you can see different tabs are given. So like if you are not that value, so you can also simulate your project. You can visit at the material software, different researchers, they publish their papers. You can collect your files or results or data. Then you can put one by one in the each of the tabs in it. You can put, it is a editable tab, unit or different things you can give in it. Same for the C60. Like you can see that have the different C60 homolumo value, different defect density, and what the actually meanings. So dielectric constant that you have changed 4.1, that have 35. So it is just a theory parts. It is difficult to explain each of the things in the major way, but in the soft description that we can say, for the each layer you can provide different electrical data, how the electron and hole move and what is the defects or how they recombine. So you can provide in here. And basically when you want to study related to this, you can visit on the manuals, each of the tabs, why they are using. So something that I've given. So it's just for the electrical data that we have provided. But when you move toward this electrothermal setting, it is only for that data that you have provided. Now you move toward the modes. In the modes, that means to say module, where you can provide for the whole solar cells that you have created. Now it will run in the electrical module. So it is an electrical operating voltage that you can give. If you want to change that priority like ground or voltage, you can change in here. Temperatures, it is the operating temperatures. And that models you want to set like trappings or different features, you can activate in here. Excitants. Excitant, like you have selected in here, that's 1 minute. In the excitant traps, if you provided that parameter, then you can activate in here because it will calculated your result according to your that input parameters you have provided. So you can give in here tabs. If you want to provide that the external loads or in this solar cells, you can also create in here. It is just a simple setting that you have provided. But now if you want to shift according to that ranges, but first I've just simulated that results. Like it is an electrical profile result band diagram. When you click on this band diagram, x-axis, y-axis, the same ranges that I've given. Charge density, charge generations, current, electrical field, mobilities, potentials, recombinations, trap capture. Same you can import their image, their data, and you can verify according to this. It's just an electrical profile result. When you click on this, you can see separate results for that solar cells that I've given. Built-in voltage, maybe it is too much high for that value or things, losses or range. That now you can select in the SIP modes your range, where you can set your parameters according to your range. You can see different settings that you have provided, and you can shift. Like first we shift the voltage, then you can understand what is the actually meaning of this shift tabs.
Excuse me, sir.
Yes, ma'am. Yes, sir.
Sir, as you mentioned about the defect analysis, right?
Yes, ma'am.
Sir, is that keeping the defect analysis for the each material is good, or if we remove also it is fine?
If you do that, each material defects or like for in this SETFOS software, if you do that each defect analysis, so it will be good for that, because losses or different things you will calculate one by one, so you can get accurate results, right? So therefore that have tabs in given, I think it will helpful toward that defects or different things.
Sir, if we remove, what are the drawbacks, sir?
What's up?
Sir, if we remove the defect analysis, what are the drawbacks?
Maybe that yeah, you can see that results when you change that input parameters. So basically, solar cells that were made for that power conversion efficiency, VOC or short circuit currents. So maybe it will when you chooses that defects, it will give that inaccurate result for the PCE, like any other 23% that you found. When you included the defect, it will definitely calculate your results, but maybe it can be wrong or right, that we can say as the technicals
Yes,
for
sir.
the set point. We can't say that it is a right, because you can't give that any parameters, but you simulated, so result will definitely come, but you can't say that it is a right or wrong after the validations, because when you move toward the theory parts, so you need to explain each of the things one by one. How do you are calculated that your PC or VSC, you included that any parameters, traps, excitants, recombinations, or you directly calculated that results? Like if you not included that electrical material files, maybe the result will come different, but result will definitely come, but maybe the result will come separate on this. Basically, number of the things that we also not provided in here. Like I will
Sir,
show
can
you.
we calculate? Hello,
If
sir.
we get
Like this, we have not provided most of the things. Something that we have given, that's we have that input parameters files.
Sir,
Like
can we
C60.
calculate series resistance and shunt resistance also?
What, ma'am?
Series resistance and shunt resistance also calculate?
In the SETFOS softwares, a
Yeah.
result like a loss analysis, you can calculate it in the LAOSS softwares, ma'am.
Okay. In that software, we are not using. We are not
You
calculating shunt
can
resistance.
you can provided that parameters, like
So can you show?
like external loads, if you want to give in here, you can give. But
Okay.
for
Okay.
this loss analysis, you need to move toward the SETFOS LAOSS softwares. It is a design for that loss analysis. Maybe
Okay.
in the
Okay. Thank you.
6.1 versions, that will features will come, because they are working on this. But in the
Which
loss
version?
analysis, it
Which version is?
6.
Which
SETFOS
version is good?
6.1 is coming. No, now it is a good for this SETFOS 6, but they are working on that different parts. Maybe that loss
Okay.
analysis or different things also will come on the next version.
Okay. Because experiment in that experimental duration, we have losses. So many losses.
Yes, ma'am. Yes, ma'am, you are right. So we have also that softwares, LAOSS softwares, where we calculated the loss for each of the electrode or layer wise. You can do, because it is
Which soft
designed for the LAOSS softwares. Ma'am. 1 minute, I will show you.
is this separated?
It is a separated. They have the different software. It is for the solar cells, and this software is designed for loss analysis and PV module simulations for the large area.
Okay, thank you, sir.
So this software you can move toward this for the loss analysis, and it for this device solar cells Webuline and built-in voltage current balance device currents. You can see this device current, electrical power, power conversion efficiency. So different features that we can explain on this. And we have that softwares And they have projects like it is a two module that we have. So if someone working on that thermal modules, we have also this. Like it is a thermal modules. We have that new modules, thermal modules. We can create on this, but we have the less time, so I can directly explain about this. When you move toward this glass, you can see thermal conductings and thermal boundary layers. You can set thermal boundary conditions like air tops and bottoms. For the environmental basis, you can set boundary conditions. Glass as the thermal conducting, then you can provide one by one that thermal conductivity, how the heat flow. For the ITO, you can provide in here. PTA, you can do in here. So you can do that one by one, each of the thermal value in here. Thermal conductivity, heat capacity, C60 and BCP, and then CU. So it a whole layer sets, you can provide thermal data that we can say, like first as the absorption modules you follow, where you provide the optical parameters. When you move toward the electrical diffusion module, so you provided that module electrical parameters. When you move toward that perovskite and thermal, where you want to calculate your temperature related parameters, so you can move toward the thermal results, and then you can visit like this. Average temperatures, heat flux, and heating powers, how they're calculated. Heat flux, heating powers. You can also collect their results and any other heating source that I've given. When you zoom it like this, so you will see. Temperatures and thermal powers. For the each layers, you can see like active absorption layer, how they are behaving. So when you check that results or data, so you can understand what is the actually that so you can do in the thermal. So that new modules are the best things for that thermal integrated or thermal profiles where you can do. So and like if someone want to create or do like a transient analysis. So we have that transient analysis projects. Like in the transient, like we discussed about the steady states in the SETFOS that have the three modes you can see: steady state, transient, and then AC calculation. So if you want to do that type of properties, hysteresis curve or time related or frequency related, so you can move toward the AC. So when you click on the transient signal, all the things in that site, it will same. Like you can create the projects, same for this. And when you move toward that modes, so in place of the steady state, you can change that the transient. And when you move toward the transient signals, you can see electrical transient data. and steady states and ramps, where you can set range from and to. And what is the actually scan rates? Then you move toward the ramps from, and then you can move toward the to, and then you can set at the rate. And at the bottom side, you can see what is the voltage. And not only this voltage, if someone want to set for the illuminations, you can also set the illuminations range. And after this, when you setting this transient signal preview, according to that, your result will come. When you simulated that built-in voltage, time steps, you can see that results zoom wise or collected, photocurrent step contributions, absorptions profiles. It is a passive optics result we have already seen, but currents, transient data. For the 8 recombinations that you have followed, you can see at the bottom side. It not only for this one layer, each of the layers, how they're working, so they're provided time related thing that you can see in here. And you can also zoom like this. So it is just transient data calculation. If you show only for this, only you can see illumination transients, electrical power, like this. Voltage or currents. So it for the transient steps, if you want to work on this steady state, after the transient calculations part. But if someone interested on this AC type of calculation like capstance, so you can move toward this. It is one of the simple examples, like we selected at the gold, PPV and calciums. And when you move toward this electrothermal settings, AC part that we're given, and directly you can calculate the results. In the frequency, when you to move toward the AC, you can see how that setting they have provided. And when you move toward this amplitude you select. When you select the steady state, that have different things. When you select the transient, it has the different things. But when you select the AC, you can see what the actually amplitude and what is the frequency that you want to set. You can see different range you can provide in here. Linear log, elements log, random logs, list and files. From and to, and then you can provide the steps. And then you can move toward the one by one AC results. I'm just showing that example, but when you follow that one of the projects, you can change only the tabs and then you can provide one by one inputs, AC currents, AC current phase, capacitance with the frequency, axis, y-axis, you can change, normalize, conductance, conductance competence, impedance. So it is too much big software at that AC charge density, all curves if you want to see, and the real or imaginary that you want to see. Can see, you can collect that results. If you want to shifts or recur how they are changing, so you can also see AC currents, AC current amplitude, AC current, AC electrical fields. Band diagrams, charge density, currents, electrical field, mobilities, and potential. Not only this, if someone want to work on the interface, like we have discussed about that hoping model, how that hoping features you can introduce. So I will also show you. Like you can see, when you activate that interface tab, in bottom side you can see it is a layer stacks editor tabs, and when you click on this electrical interface, enable is your excite and dissociation for this interface. Hopping models you can introduce in here. Like a hopping model basically say it's some layer that have a insulated or barrier they have created, you can use. So interface traps, you can also include in here trap density, trap energy levels. In between this, like it is a physical conjunction between this NIO or mid ITO, and interface recombinations value you can also include. So according to this, one by one, you can see that so whole of the result, it is simple result related to the electrical data. It is not at the optimized. If someone want to see that optimized data, we have that optimized result as well as, like we discussed about this. One minute, I'm going to show you one of the optimization example. Right in here, you can see. Like that one of the same layer structure ITO and that file we have created with this electrical interface. How you can optimize your structure when you activate absorption and depth diffusion. You can follow that same layer stack you can create. Then you can create the thickness. One by one you can provide that optical data. Then you can provide electrical data. Simple steps. You can activate absorptions parameters and then you can provide that value. And after this, you can give in here the electrical data. You can provide that value. And in the optimization tab, when you active, you can see you have selected two layers. Not only that layer, it totally depends on the users, which layer they want to set as the parameters. And then you can send here the targets. It is just for the tandems example. So I'm just activate that tandem. If you not activate the tandems, you can set your own targets in here. Electrical key figures, files and plots. So it depends on the users, which type of files, plots or results they want to set or targets you can do. But as the tandem examples, you can see minimum photocurrents or maximum photocurrent you can set in here. And it is the parameter tabs, minimum value and maximum value. And when you simulated these results according to that only selection, it is the optimization tab that we have discussed. You can simulate your results and reflected color you can see in here. Para optimizations result you can display at the set value. And in the bottom sides, you can see different absorptions file, different layer absorption parameters. And when you want to compare with your result with another projects, you can also do simple click on the control button. You can see two projects you can compare with the click of the control, and you can see how the too much results or layer exhaustion. Not only this, you can click any one of this and then you can compare for this. So it depends on the user. So a comparison you can also do in here, and optimization tabs. First you need to set your parameters and then you can set according your target, and then you can extract your results according to this parameters. So it for that optimization. And it's that we have discussed absorption, drift diffusions, and optimizations modes, AC calculations. But when you move toward that scattering modules, like emission and scatterings. So emission, just you can calculate emission parameters, and scatterings settings that you can do for the scattering modules. When you click on this result part, so before start of this, you can see air, glass, ITO, STL, and ETL you can take as the layer and thickness. But when you activate that modules, so like when you activate electrical modules, so that type will active. So similar when you activate the emitter, so you can
Hello.
see. Yes, ma'am.
Why use cathode? Like which layer is it?
Ma'am, yeah, it is a emissions and or scattering projects. We are not included in here that's depth electrical parameter. We have also the electrical. It is just a simple examples related to this simple
Okay.
parameter that we have calculated. When you move toward the advanced, we have also that. So it is just I'm showing the modules because we have that less time. So I need to cover. Like it is a scattering modules, simple tabs. Like if you activate that electrothermal settings, so you can also include, like you are asking how we add electrode. So you can also add electrode, not a issue. You can activate that tabs and then you calculate. So then result will change definitely. But it just you taken the emission and scattering parameter because you imported your emission files in here. Like this, you have imported one of the emission files that supported photoluminescence spectrum files in here, like you can see photoluminescence spectrum files, and in bottom sides you can see that range dipole distributions. So different settings you can provide. It just settings for this, and mode you can also set spectral dissipation power analysis and mode analysis, and it is a scattering settings that if you activated that layer scattering, you can see different scattering features or tabs will active particle BCDFs, monodisperse, and quantum dots feature. So number of the users that have asking that question different. So we have that different result according to this angular scatterings features, blue index. It is an emissive property only for this. You can see blue index, emission parameters for this layer stacks that have given in here, color diagram, color rendering index, correlated color temperature, delta, emitted color of this initial layer. It is just a layer name, but when you move toward this emissions file, you can see that have supported that photoluminescence spectrum files. According to this result will come. It for the scattering results. So different features, different optical integrated. So when you move toward the interface, not only the electrical interface you can add, if you want to add a scattering interface, so you can also add any other scattering interface. Like when you enable drift diffusion modules, ma'am, so you can see electrical interface or interface for the scattering, both will active. So one by one you can do. But when you activate only this scattering, so you can see coated interface or scattering features, imports files or different things you can provide one by one. So according to this, scattering result will come. And it's for that one of the OLED examples, like someone working on the organic light emitting diode, emissive parts, and in here that we included emission and electrical. In here that we included electrodes or aluminum electrodes, ground. So when you selected these scripts, the different value we have provided and emissive layer that we consider, and you can see that results. At that previous, we included emission and scattering, so only that result will come. But when you included that depth diffusion and this module, so according to this result come, electrical result included. And one by one, you can check any other results. And electrical profile like band diagram. So bottom side, you can check current efficiency, luminance, peak emission intensity. You can also copy or compare. Passive optics voltage, spectrals, and spectrals results, emissions, normalized emissions, white emissions. So it is a too much big software. If someone start working on this, so they will get exact idea how they works, how they are behaving, different projects or parts. And we have that more softwares like LAOSS softwares where you can work for the PV module simulations, series resistance, and some features for that loss analysis you can do in the SETFOS software. But for the more advanced, you need to move toward the LAOSS software where you can calculate every shunt and different losses. So anyone have that query, they can ask. Another, I'm going to show that FLUXiM and LAOSS software, some of that parts. Yeah. Please ask any query if you have. If someone want to manual or tutorials, I will provide on the WhatsApp so they can check their features of the SETFOS software.
Yes, I will. So how about the 2D materials? How good it will be?
WhatsApp.
Materials, can we work
So
on
your voice is not audible to me. Please speak.
Can you hear me?
Hello.
Yeah, can you hear me now?
Yeah. Yes, sir.
Yeah. How about 2D materials? Can
Two 2D materials, sir.
2D materials like graphene, or
Can you write on the chat box, sir? I can
Sure.
see them, please, so I can get exacts. It is a FLUXiM website. So if someone want to visit on this website, it is a parent company of that software. So you can do and you can research on this OPIC software, SETFOS software, LAOSS softwares. Like LAOSS softwares, it is a something that we can discuss. It is 3 modules. They have divided electrical modules, thermal modules, and optic modules. Like SETFOS working for the small solar cells, but softwares, it is large area organic semiconductor simulations. Basically, you can do for that large area, like you can import your geometry directly, then you can provide a difference value. and then you can simulate your results. Basically, the three terms that are given in here, you can create your geometry, CAD, AutoCAD, or LaborCAD, different tabs you can apps you can use. Then directly you can import, and then you can simulate your projects. It working on the finite element analysis parts, electrothermal modeling that you can do. So you can design or optimize your electrode, reduction of the electrical losses, non-ideal effect of the OLED and solar cells, understanding that OLED pixels, thermal modules, electrical that you can couple in here. So it is too much big for that PV module simulation that you can do. So it is a large software. And not only this, you can see we have the number of the products. So when you visit on the FLUXiM, so you can get a lot of the idea about how you are working. Ask any question if you have. Yes, ma'am. You can also collect say, your different tutorials from that YouTube channels. I'm going to show you that YouTube channel as well as Impulse Technology. You can see different tutorials that have given, so you can also get a lot of the idea how they are different from the escape 1D, because I think number of the users that are working on the escape 1D, so you can differentiate in here directly. We have that a lot of the tutorials that we have added. You can check that playlist SETFOS tutorials. So you can check that playlist where we add different solar cells, OLED optimizations, emission zone fit, multi-layer coatings, solar cell scatterings, 4-terminal SETFOS installation, degradations process of OLED, and IIT Madras, Behrampur University, or different institute that publish their paper. You can also visit on the Google Scholar as well as. Anyone have that question? Please ask. Someone asking that we have the constant with respect to the thickness of material for the simulating the device. You can select according to your, like we have selected the thickness in it. So you can also strip your different range. We're just selecting the example value. And not only the follow that simple thickness. When you visit on this strip, you can see that layer. And thickness, if you want to vary it, you can vary it in here. They have no limitations any for the thickness that you need to select only that range. You can select any one of the range unit that have given. You can also type type your query on the chat box so I can also explain. For
Sir,
the
could you
trial,
share? No.
yes, ma'am.
So could you share Longi experimental data? How to simulate and run, if
Logi
possible?
experimental data.
In
Sure.
first slide, you share
Ma'am,
26% of that efficiency.
I will connect you, ma'am, after the session. You can directly message me.
Okay, for sure. Thank you.
Please type your query. We have that time for the query. Evolutions license, for the evolutions license, you can connect me after the session on WhatsApp. We will definitely try to provide you the evolutions license.